Oh, sorry. I didn't. Maybe I lost this. And anyway, so that I should give you the homework, right? The first one announced, and then it's important for me to give you the homework for you to do some exercise, so that from my point of view, it's important that you need to do exercise, not just simply listen to the lecture. This is very critical. From my point of view, without doing homework, you probably cannot learn all this kind of knowledge and things. So that I give you, of course, I really carefully to pick up those homework and then add additional reference for you to make sure that you can really have some understanding about that critical issue. Let me quickly. Sorry, I forgot to attach this one. Let me. I don't know if I didn't attach or not. Huh? Let me see. You should attach. Anyway, let me attach it again. No, I didn't attach. I'm really surprised. Okay, anyway, so this is the homework I try to ask you to do, but beyond homework, I have to let you know that it should be something useful for all of you to think about, right? And we have talked about this kind of how we can construct the MCK model, mass spring system model from sound mechanics and things, so that again, we only learn this kind of one equation, right? And then so that we try to learn sound mechanics, how to determine equivalent spring constant, and then we determine equivalent mass inertia, and then we understand about the typical damping from physical damping from dry friction and material damping as the rate damping. So that here we have viscous damping, and then see this kind of dry friction, and see another one is material damping, right? So that this is something we have described, and then of course here we move to the another important thing is how can we really look into this kind of vibration engineering, right? So that here I shall show you about some of I think practical problem, right? For example, you have a ship in Hong Kong. We have so many this kind of ship, right? To for transportation of product, and also maybe ferry and many things. So that in this case, at least this gives you some example. Why, if you have certain ship, and we give you this the weight, the mass, and polar mass moment inertia. And next one, of course, in reality, our this kind of propeller is have actually more complicated structure. So that then the question is, can you try to look at this kind of how to determine torsional vibration response of the propeller if this engine has certain kind of speed, right? Certain harmonic, this kind of oscillation and rotation. So this is, I think, is give you some example. And of course, this one is another thing, quite common thing, right? So if a precision like manufacturing, like a grinding, right? So that in this case, if you want to have a certain kind of a good for first a maximum acceptable displacement, and then can you come with some idea about the design of this vibration engineering, right? Basically, what the thing is based on the maximum allowable this kind of vibration amplitude, and how can you come with the right design so amplitude can be small enough. So this is something really, I think this depends on the requirement. Hey, I don't know if you, for this grinding, what's the application of grinding? Huh? Grinding. Huh? For this machine. Any idea? Huh? For this grinding, right? What's the typical application in manufacturing process? Process of what? Yeah, but I just told you that this is one of I believe all of you have seen this kind of machine in machine shop. So that this kind of grinding is quite common in the industry. All right. I will give you some interesting company who do the grinding for many maybe more than 50 years. There's one small company in Taiwan, near the Taipei, and then they're working on grinding for more than 50 years. So that in old day, the grinding for, like when they start a business, the grinding is maybe for the home, this kind of, those kind of like product in the kitchen at home, right? Knife grinding. And then recently they invent some special diamond grinding, and then they really work for semiconductor industry to help the TSMC to make a nanometer smooth silicon surface on silicon wafer. Huh? So that I just tell you, this kind of grinding has a very low end application, but if you try to continue to do this thing, and then it can become important for semiconductor industry. I just tell you that's one interesting company who has really worked on this grinding machine for more than 50 years in Taiwan. You may want to surprise. Do you know the company? Huh? Anyone has an idea? Zhongsharen is you can look at Google. Yeah, there's a interesting article, right? So about this Zhongsharen, basically it's more than 50 years ago. It's a small company, and then this kind of thing. There's an article to describe about this small company. Now they're using diamond grinding for their business work with TSMC for nanometer. Nanometer, this kind of grinding with the diamond. Okay, I just tell you this is interesting, right? So then kind of vibration will be very different. Diamond grinding for CMP process used in this kind of semiconductor wafer industry. Actually, TSMC. You were surprised, huh? Nanometer. This company is for 50 years for those very low end, huh? About grinding of knife for your mother, huh? Let me see. Yeah. It's quite amazing. They look at so many Zhongsharen. Yeah, they look this one 50 years and then continue to improve the grinding technology. Now they make a big business now, big money. Nanometer, but because it depends, right? If you do grinding for the knife for your mother in the kitchen and grinding for the silicon wafer, it's very different. Okay, but what's different? This kind of amount of vibration is very different. I think this is here. I just seeing is give you definitely this kind of vibration amplitude is not for semiconductor. Why? For semiconductor, more likely it's go to what? Nanometer. So anyway, so that it's something interesting. There's an article talk about this thing. More they call the grinding, right? They use this kind of grinding is a thing. I will give you some interesting article about the recent like article talk about this company's industry working for grinding for 50 years from low end to the more advanced this kind of nanometer grinding process. Okay. And then this is another quite interesting important thing. Right? We mentioned in the first lecture about vibration, flow-induced vibration problem for Tacoma Bridge, right? And also we do have students from AE, right? So aerospace engineering, and then so that for this kind of flow-induced vibration, so that it's also important for this kind of a car, automotive industry, so that once you have this antenna, and then they tell you about there's some special telescoping antenna, and can you try to think about this kind of thing, determine whether the sounds this kind of flow-induced vibrating voltage shedding, so that they give you this kind of a two frequency, right, and voltage shedding, and for this speed. This is something is I think one of quite interesting and important issue, right? Still, flow-induced vibration is still quite commonly used found in the industry. And another one is look at those kind of vibration of the automotive industry, right? If we have a wheel and lift spin of a car, right, and then traveling on the bumpy road, rough road, and then so that if you know the mass of the car and the lift as a spring constant, and then also give you this kind of 1 and 2, the wheel, and then in this case, if this road condition can be simplified, right? And as this very simplified way, defined as y equals this kind of 0.1 meter, and here this kind of bumpy road, right? And then so that can you find the critical velocity of the car? Of course, I will show you who is control the world for this kind of vibration engineering for the car. It turns out as one big company from Germany, right? Best. They have this kind of interesting TPU, expanded thermoplastic polyurethane, and it turns out their market is huge, about $73 billion for this kind of a TPU for vibration control of a car. So it's not small. Here I can show you this kind of thing. They're really one of a key player in the industry. Let me show you. My vibration and noise. This company is huge, and recently, actually announced that invest 10 billion euro in Guangdong province, 10 billion to build additional plant for their product. 10 billion, 100 亿, 10 billion euro. Can you imagine? This is one of a huge, this kind of huge big company, international company. It's not small, it's a huge business, okay? And of course, I give you some additional reference about their company product, right? John's bumper, and they show in the video, coil spring isolator, and this, they really control the world market. It's a one of our top player in the world, number one, number two. It's a not small business. This is a huge, and also the additional summary. Actually, I really try to. I download. I pay this kind of thing, and then I already done all for your reference, so that now this kind of thing is not free actually, unfortunately. Anyway, I already download for you, and then so that let me quickly show you this part. Yeah. So it's something from my point of view is good for you to look at what we say is a real the kind of a product, right? Although here I give you some, but anyway, I do think it's worthwhile. Open the file. So that they do, you see, they really is one of their big business division in one of this big company from Germany, and they use in automotive industry a lot. Yeah, and I do think you try to look at their anyway. So that the key thing here is they have I show that particular one for the car industry. So that the efficiency, comfort, vibration control, sustainability, and more efficiency, so that they have so many this kind of polymer, right? It has for many different parts in the car. Here, of course, I have to just emphasize this part, but actually they have a lot more. Yeah. Okay. So that again, they say this particular PUY, this product is they can say every second car they have their product in the world. It's a not small business, it's a huge business. Yeah. Okay, so that well, this is something for you to do homework. I hope you understand about the real product, real vibration engineering, and then I would say it's something useful for you to think about this thing. Although this is a simplified, right? Simplified problem, but look at the real product. Of course, if some our PE student work on the project for robotic system automation for our Hong Kong CRC project, so that you may need to think about if you want to use this kind of the product, right, for vibration control. So that something I do think this is important for some students who are working on the real product design prototype. Okay, so that I don't know, do you have any question? So that this is give you again. So what we care is why this is important? Because this polymer, right? Remember, polymer with higher damping, right? Remember we talked about in our lecture notes, so that we have to use this kind of many car, maybe we use some metal for our car, make our structure, and then the damping of the metal is so small. That's why in this case we may need to introduce some of viscoelastic this material, right? This material to make sure that we control the vibration amplitude, so that the people inside the car will feel comfortable. Right? If you don't use 100% metal for your car, people inside will feel very bad. So that at least now I give you some real this kind of product from this kind of big international company. Again, so that they best actually invest $10 billion. It's not something. Did you at least just see why best invest $10 billion? In Guangdong, euro. in Guangdong. It's just recent, I think last week in Guangdong. It's a huge empire. You look at you see, best built 10 billion petrochemical plant. Why is Guangdong? Why? Here near this kind of Hong Kong, Shenzhen, Dongguan, and Guangzhou, you have many company or electronic product. Also, what new electric car industry? You know how big is this kind of new electric car industry in China? How big? Recent news they also announced that now China is export the second largest in the world to produce a car, most likely new kind of electric car. So that there's a series of car maker in at least in this Guangdong province. They try to. That's why I can see that this company, German, this kind of company, see opportunity for their product to be used for the car industry. It's not something I tell you that they do has a huge business. Big now, this thing in mainland China is not small. It's a huge business. Yeah. So that for those student work on automation, robotics, so that this something maybe you need to look into more detail about their product, right? To see if their product can be useful for your own thing, right? This is not only for automotive industry, but also for many other things. This is something I think is worthwhile for some of you to look in more detail. Okay, so that I don't know. Do you have any question? I do think this homework something. Although you do some exercise, but I do want to provide you some practical application of this kind of our course content and the homework. Again, do you have any question or comment for this kind of thing? Okay, if not, then I think we need to go to our lecture now. So that's on. We have talked about this kind of vibration engineering to the chapter 3, right? So key thing here is chapter 3. Now we really try to look into this kind of vibration as a function of time and look at much more detail about this kind of issue, right? So that again, for our vibration engineering, our primary is we try to think about how can we try to engineering this kind of system, MCK. C in here is what? This one, our damping. Damping is something important. That's why in your homework, why we try to introduce this kind of vibration isolator or vibration damper, right? Using some polymer material like TPU, like this big giant company product to make sure that we can really achieve some good performance, right? So that this is something I think is useful. And again, you see, we just show you this kind of homework, number 2, and also this thing, so that the typical sharp sober, so the damping ratio is high, to make sure that you can have do vibration control, right? If you see those metal, what you see, damping is so small, so that without this kind of polymer, right? Like what we show you TPU, and then in this case PU. PU is one of a very common thing. Okay, so that this is something I just tell you that in this case it's critical, right? To add this kind of big viscoelastic polymer as a vibration, this kind of damper or vibration isolator. So it depends on the technique, right? How you are going to add additional component, right? So that something is important and thing. Okay. Again, so that I again try to give you, if you want to look at some again, look at this for I do recommend try to look at this company's summary about their product. Okay, so that this is something useful. Of course, it's not only useful for automotive industry. If you look at this kind of German company, they also use for what? Huh? For your shoes. Adidas shoes also use this kind of product from this German company, right? You for good sports shoe, you most likely you have some viscoelastic polymer, right? Adidas actually use this kind of German company to make their good sports shoe. So that let's try to give you something important thing for you. Okay, and of course we already mentioned that for us, if you want to do more carefully, first is damping, right? How can you measure the damping? So that one thing is if you can have a vibration sensor to measure this kind of vibration amplitude and function time, your smartphone like has the motion sensor, right? If you can measure vibration like the motion variable observation, right? And then a function of time, so that in this case you can easily try to get this result. So that I do hope that all of you have installed some kind of smartphone app so that you can really get this kind of result. Not only what I show here, right? If you have smartphone and then download the smartphone app and then so that it is you can, right? You can try to look at this thing and then this my smartphone show you this kind of real vibration amplitude and functional time, right? So that by the time, I don't know, if you try to play with your smartphone, the motion sensor, and then it can be useful, right, for you to look in this kind of issue. Okay, so that again, this is something I do think is worthwhile for you to not only look at our lecture content, but also to see if you can really look into this kind of smartphone as tools for to understand this kind of vibration. Okay. Of course, we also mentioned that when we try to study, because if you assume our mechanical system is a one degree model, or NCK, one DOF model, and then we have exact solution, right? Vibration and functional time can be determined in this way, right? And then, so in this case, we can use this one to categorize this thing. Eventually, now it's clear if you can measure using vibration sensor, right? Measure this kind of amplitude, a functional time, and pick up two peaks from your the data from your vibration sensor, and then take a ratio of these two peaks, right? That means you have this, right? Maybe number 3, 2, and 3, and look this ratio, and then this may be x2, x3, right? And in this case, we can easily show that we can link this kind of our data, right? The ratio of 2 peaks to this kind of damping as linear function. If damping is small, then you can simplify it this way. If not small, then use this formula. You can using so this is a practical way. We can do vibration testing, determine our important damping in your model. right? Yeah. Again, so this formula, what's the limitation? We linearize, right? We assume this thing so that you see. So if the damping ratio is probably less than 0.3, okay, so this regime probably is good enough. But if damping ratio is bigger than 0.3, you may need to use 1. So 0.3 is one of the important things. You may want to look at what? For example, look at our previous slide. Which kind of condition is 0.3? So that in some case, right? See, so that I would say majority, if you, for example, building, you see, 0.3, most of this Y is okay. Okay, 0.3. But for this kind of automotive, the vibration damper or over there is not good. So that this at least give you some idea about how we can use this simple formula, right, to determine our measure. This is delta can be measured, right, and we can determine our damping ratio. Okay. Anyway, I think that's something we last time we'll also show you this kind of example. Of course, we do have one student try to describe about some little problem of this solution. Well, I had to believe this is a simplified way to analyze this problem, so that if you look carefully, and then this solution maybe is simple approximation, while the real thing you may need to look at a much more detail, right? Okay, and last time we also mentioned about this kind of vibration control for a motorcycle, right? So that that is something we just quickly give you the thing, right? So that this also relevant to our homework example. So the key thing here is practical vibration engineering is what? We give you some requirements, see? We'll give you requirement about what's the maximum amplitude, right? And then can you determine our required, right? This vibration isolator, vibration damper. Basically, this is related to your vibration damper, right? Vibration absorber, or this shock absorber, right? Shock absorber, and then so C shock absorber, so that we based on requirement, different industry have different requirement for vibration requirement, and then based on different requirement in the industry, we try to determine what's required at K and C. So that is one of important vibration engineering for the real product design. Again, the same thing can be happen, as I mentioned, like more than 10 years ago, there's several student DJI, those founder, co-founder take my course as a question. If you have a drone, and then how can we do vibration control for this kind of drone for DJI, the product prototyping, so that that this kind of thing is also can be applied for real product design. So what do you think? If you have this kind of a rotor, right? Helicopter or the drone, and then not only one rotor, I mean multiple rotor, and then how I go into vibration control so that you can take a good picture and video. These are all similar vibration engineering thing for real product. What do you think? If you have this kind of some kind of motor and rotor, right? And then how are going to do the vibration control so that you can really make a good system? I just want to ask any idea. The same thing, if you have certain kind of we talk about one rotor, right? You have a one rotor and then you have helicopter. So the helicopter here simplify the view, helicopter. So this is a one rotor, right? And then you have engine, right? You have engine, and then so that and you have engine somewhere, so that so you have rotor, and then you have engine here, engine, right? So that in this case you have vibration problem. So that in this case, if you have some camera, right? Typically, for the car, drone, unmanned thing, you have a camera, right? Detect camera, right? And then in this case, you need to think about how I can add additional vibration, this kind of isolator, vibration damper, C and K, so that how I'm going to add this thing. So key question is, design problem, design problem, right? How to find the right design, the best design of KC and CC, right? Basically, I would say vibration control, right? Vibration absorber and CC, vibration absorber, This is important for big for our student aerospace engineering and small drone, right? Drone and so that they all face the same issue. Okay. Any idea? If you have this kind of engine, and definitely you have some vibration problem. But key question is how you can work on this kind of a design, so that I just tell you what we mentioned now here is not for fun. It's can be important for real or this thing. Okay, so that anyway, I think I will skip this part. This time we mention here, right, as an exercise. So of course, if you assume this kind of a 1 degree feeder model, then we can use those kind of this kind of vibration data, vibration motion sensor, right? It measures this kind of vibration and functional time, and then determine our damping ratio, normalized damping coefficient. And then in the case, we can really try to determine all this maximum vibration amplitude. So that that's something is an important thing we discuss this time, okay? And then eventually, again, what is the most important thing? The most important thing is here give you some idea. You need to think about how once we give you the vibration amplitude as a requirement, what's the way to determine this unknown, the K and C, right? Add additional vibration absorber, so that you can really try to control the vibration amplitude or vibration velocity or oscillation. I think it depends on different product. So of course, here is only very simplified way. We do have one chapter and show you about how we can work on this kind of vibration standard for different industry. So that if you do you have any question you want to do? Basically, I can give you, if you want to look at those kind of issue, for example, we do have some chapter talk about vibration, this kind of a standard. I think is around here, chapter 9. This is will give you vibration testing, and this will give you some important thing for you. Okay. So anyway, if you want to look at this issue, so that different product have different, probably you look at different standard, industry standard. For example, for smartphone like the app, your iPhone, what's the vibration requirement? There's the industry standard JDEC, okay, for this consumer electronics, right? For different the kind of product. Again, I told you they're different standard. Okay, so that I just tell you. And for the car industry, what's the different standard? Huh? There's certain kinds of standard. No, okay. Anyway, so I just tell you that at least you may need to look at. I have some additional lecture or discuss in the near future, so that at least here I just give you something. Here assume this amplitude has been given, but in some case you may need to look at this kind of industrial standard. Okay. Okay, so that of course last time we also briefly mentioned about this issue for this kind of electromechanical analogy, because sometimes if you work on some very sophisticated, for example, self-driving car or drone or robotic system, you involve some electrical mechanical system design. Sometimes you may want to try to convert mechanical system MNK or MCK into electrical like part, so that it will be interesting and useful, right? Mechanical electrical analogy. Typically, the force can be equivalent to voltage, mass, inductance, damping, resistance, right? Spring constant and 1/c. So this is the typical way now thing. And of course, last time we also show you that many times when we studied some vibration analysis or experiment or something, and if our equation motion is come with this kind of second order differential equation or different equation system, then we may need to do this kind of if one different, we can have exact solution. If two different or much complicated, then we may use computer to solve this kind of equation motion. So numerical this method becomes so important and useful. Why? So that I just today you know that this is quite important for all of you to think. Right? Of course, as mentioned that typically we discretize differentiation into the difference, right? Dx becomes delta x, dt becomes delta t, right? So that if this kind of time step become very small, then we can really try to get this kind of solution. But if the time step is too rough, then your result is not good. If you try to reduce the time step to much smaller, then in this case, you can get a much fine, more accurate result. So that this is something easy. If time step is increased by 1 order of magnitude, originally 0.5, previous 1.5. Why? It's a 0.05. Same, the prediction will be more accurate. Right? That is something. And then, of course, in reality, when you solve the kind of our equation motion for vibration analysis MCK, then sometimes or most time you may want to reduce this kind of second order ODE into the what? First order ODE by introduce this kind of new variable. X2 is equals velocity x dot. Right? In this case, so that the x double dot acceleration will be x2 dot, right? So in this case, I can really try to simplify into this kind of two first order differential equation. So in this case, we can easily use MATLAB to solve the problem. So this is something I think important. And of course, when you write this kind of first order equation ODE, sometimes we define A is a matrix, right? If 2 times 2, then it's similar here. And then our X factor is related to X1, X2. And then in this condition can be to here. So in this case, I can really solve this kind of equation motion in the vector equation here. And of course, we already show you about this kind of, why we write down this kind of our equation motion, right? Second order MCK into this first order, then actually MATLAB can easily help you to solve this kind of thing in very easy way. So important thing here is what? We need to define our function for that kind of ODE. We need to define this function and then so that then give you time span, maybe 0 to what? 0, maybe 10 seconds, and initial condition, so that in this case we can get our t vector and y vector, from this solve this kind of ODE or ODE system. I think I do have some example. If you look at our we give you some example so that you okay. I should try to give you some of the few examples now, right? So that you are able to at least last time actually I already showed you the example, right? For how you can find this vibration amplitude as function of time, and then the same thing we can easily solve this kind of a problem, right? Anyway, I think I should try to give you some example for you to do exercise how to solve this kind of ODE. I don't know, do you have any question or have ever used this kind of MATLAB, this kind of something is worthwhile thing. Now, of course, we need to go to another important topic, respond to harmonic excitation or force vibration. So this is one of, I would say, very important concept and part for this vibration engineering. Why this is important? Well, I'll show you why. So that I also have the video. Let me show you the video. The key thing here is we have equation motion, and then the important thing is that we want to what? I will skip the part. That's we want to determine the kind of vibration response as function of frequency, right? So that once you have an MK model, if you have no damping, and then can we determine this kind of vibration input output response, right? As function of a frequency, right? So that is something we want to describe. I think I do have some video. Let me show you the video. Let me show you the video, then it's much easier. I do have some video for you to look at this kind of here.
In this lab, we're going to look at the response of two very important linkages. We have a slider crank linkage and a Scott-Yoke mechanism. And they're also driving a mass spring system. Right now, we have a single degree of freedom set up with one spring and one mass. This is our input. This block is our input. And this would be an output we're observing.
And they want to see the response.
And we have a magnetorestrictive sensor that records the position of this input cart as the slider crank moves. And one difference between these two linkages is that the Scott-Yoke provides pure sinusoidal motion, whereas the slider crank has two frequency components. The main frequency that it's being driven, plus twice that frequency, a higher harmonic. And we'll see that effect when we drive the spring mass damper. We'll notice resonance at two different frequencies. So here we have the slider crank in motion. We have the input link, which is the crank, and the coupler link, kind of like a connecting rod. And then we have the slider. So we have 1, 2, 3 pin joints and a prismatic joint. All right, here's the Scott-Yoke mechanism. We still have a crank link, but the crank link is attached to a slider, which drives the output cart back and forth directly. So we have 2 pin joints, then the slider joint, and then another slider joint. Again, the Scotch yoke has pure sinusoidal motion, and you can see that in how smooth this output cart is moving. But you'll note that with the slider crank, because it has an extra frequency component, the motion is not as symmetrical, and it appears to return a little bit quicker and have a little bit of pause in the motion. So here we're plotting the output from both the slider crank and the Scotch yoke mechanism. So as we said before, the Scotch yoke output is pure sinusoid, and it appears that way when we plot the measured data. And with the slider crank, you can see it's fairly close to sinusoid, but because it has a second frequency component, we have this delay type action in the low part of the curve, and a slightly quicker return action. So now we're going to look at the frequency response of each of these linkages driving a spring mass system. Before we do that, though, we want to first measure the natural frequency of the system and determine the total mass of the moving cart and the stiffness of the spring. So first we're going to do a manual test by releasing it and recording the oscillation. By measuring the period of these oscillations, we can determine the natural frequency. So to actually determine the total mass that's moving, which we need to know, and the stiffness of the spring, those are two unknowns. We have to do two experiments. So we've already done one with this mass. Now we're going to place a second mass and bolt it down and repeat the natural frequency experiment. And by observing that response, with those two responses, we can determine these two unknowns, the mass that's moving and the stiffness of the spring. So now we've bolted an additional mass to the cart, and we're going to do the same experiment. All right, so here's the response with the additional mass. Because natural frequency is the square root of k over m, the larger mass will give a smaller natural frequency and thus a larger period. So here we're going to look at the frequency response of both systems. Right now they're being driven at a very low frequency, much below the natural frequency. And as predicted by a second order system response, the output should have the same amplitude as the input and be totally in phase. So here you can see at the low driving frequency, the output tracks the input and there's no phase difference between the two. It's only a slight difference between the output amplitudes. Okay, so here our driving frequency is half the natural frequency of the system. And you can see the slider crank is creating resonance in our output mass, whereas the Scotch yoke is not. And it's because the second frequency component of the slider crank happens to be twice the natural frequency. So because we're driving it at half the natural frequency, we're exciting this natural frequency vibration, this resonance. Here we can see the output response of the slider crank in yellow and the Scotch yoke in blue. And as you can see, we're exciting this higher harmonic, and we're getting oscillations at twice the frequency that the system's being driven. And also we have a slightly larger amplitude in the slider crank because we are experiencing resonance due to that higher harmonic. All right, so here we're driving the slider crank just below the natural frequency. And as you can see, we're already getting quite large output amplitudes. So again, we're approaching resonance. We're not quite there yet, but the amplitude of the output is already growing much larger than the input. And we're starting to see a phase lag, where the output is lagging behind the input.
So this input-output response.
At resonance, this would be off by 90 degrees.
So here, this is what was it? This input is output, right? So that what I show you in this thing is input-output response. All right, we want to show. So of course, this is only show you one particular frequency, and then the input-output. But here we give you a what? Continuous, this kind of the function, right? Different frequency, right? With different input-output response of this system. Do you understand? So that this is one of quite important thing because the frequency response function. Okay, so here we try to define FRF is one of the most important frequency response function, right? And which is related to omega, or maybe sometimes they call the related to the frequency, right? Frequency in hertz. So that this is something I just tell you. This video, I believe it should be quite useful for you to look into this kind of input-output response in this video. Let me continue.
Quarter cycle out of phase. Okay, so now we're well above the natural frequency, about 50% more than the natural frequency. And you can see the output amplitude is not quite as large as the input. And we're getting close to a 180 degrees out of phase difference, where the output lags behind by almost a complete half cycle. All right, so again, the output amplitude is not quite as large, and it's starting to lag behind by almost a half cycle. So close to 180 degrees out of phase.
Out of phase. Right, you see. Let me show you this thing. So that we have this kind of thing. So the driving frequency smaller than native frequency of our MECH or MK model, okay, is in phase here. But if larger, then natural frequency of our mechanical system input output here, out of phase. So that using the video, I think would be much easier for you to visualize the real vibration response of this kind of example, this MECH spring system.
So there we're running a little more than twice the natural frequency. And you can see at higher frequencies, there's very little output amplitude.
Yeah,
and the output does lag the input by almost exactly 180 degrees.
Vibration output would be much smaller.
Okay, so now we've added an additional spring. So we have two moving masses. So this is a 2-degree of freedom system. And the purpose of this is to look at an effect called dynamic absorption, where you can tune this system such that when you drive it at its natural frequency, you can basically absorb the vibration of this system. Okay, because the system is tuned to have the same natural frequency as this system, when it's being driven at its natural frequency, you can see the vibration is totally absorbed by the second mass.
So this is called the vibration absorber. Remember we talked about the type 101. So that we add the additional vibration absorber to absorb the vibration of the building, the tall building. So that this is give you a very simplified model in the lab. Okay, so that but let me, of course, well, I think would be interesting for me to show you about that the video. Remember we show you about the video about vibration. Let me see. Type 101. Yeah, here, vibration absorber or TMD, right? So that is real. That means this is definitely is the one I show you here. This may be the building, type 101. This is additional, this kind of a vibration absorber or TMD mass.
And this one remains almost functional.
Well, I think this video, from my point of view, is a good way to summarize this kind of this thing. So that I think would be easier to use this one example to explain about this thing. Of course, let me quickly show you the basically what I show you is experimental work, right? So that of course from the modeling point of view, once you have one degree MK or MECH model, and then if you have harmonic force, right? There's no damping, and then you can easily determine, you can see MK system with the driving force here. F equals sinusoidal function, while omega is driving frequency. In the video we show you here, it's actually with the video actually show and I think I need to sorry. So basically, what we show here in the video and this one is exactly the same. But in the video, basically, is you see
System.
Right, you have a certain motor with frequency that relate to here. This one, right? This motor will control the frequency. Right, and then we want to see the response, right? The response of this MECH or MECH spring system. So that's something I just tell you. Then of course, this can be easily solved. under harmonic vibration, then we can easily determine the total solution will be consists of homogeneous solution. For the case, there's no applied force. And then for this solution is related to input force. So that this is general solution. I think you have learned about this kind of our math course, so that I do think, and of course, once under harmonic vibration, and then we can easily transform what our ODE differential equation into what algebraic equation. So that is something important. So basically, this is become the linear algebraic equation, right? And then we solve for unknown or unknown x, right? Is related to this kind of normalized input output response and normalized frequency. Okay, so that is something it would be quite important, right, for all of you to appreciate this kind of result. And of course, in general, you see, we have two parts, homogeneous and particularly. This is the free vibration. This is the forced vibration. If we have our video is related to this forced vibration, why? So that basically
right now we have a single degree of freedom set up.
To do this kind of motor. Okay, so that this is related to this particular solution. So this one related to what? Huh? What's the solution for our thing? Huh? It's a free vibration. If you have no motor, it's not applied force, no engine, then once you hear that, I see this kind of vibration from initial condition. Okay, so that I just tell you, this is something. It's not only look at the equation, but look at how it represents the real, right, vibration response. Okay. Anyway, so that eventually I can show you this is general solution in terms of time response, right, for one defeated MK model, right. And again, so that this is what we call the free response function, and then typically we plot this free response function in this way, right? So that this is the normalized input response and normalized frequency R, right? You see, so that we have when we have applied loading DC, right? Static loading in solid mechanics, you have this kind of thing. If you have some small vibration, small frequency, it go to what? Very large, and then beyond and out of phase. This is out of phase response. Okay, out of phase response when this R larger than 1. Okay, so this is the in phase response. Why? When R less than 1. So do you think? So this is something important for all of you to see. Of course, next question, can you use MATLAB to plot this one now? How? Okay. It's important. How we can use MATLAB to generate this kind of thing? Huh? Any idea? Well, I think I may try to show you now. So it's important and useful, right, for me to show you the demonstration. Demonstration of this kind of a real product, right? So that let me use MATLAB to quickly show you this kind of thing. So that from my point of view, both this kind of analysis and thing has their own value for real application. Let me quickly show you about how things. Well, how can we produce the kind of response? Huh? Basically, you need to define natural frequency, maybe 2 natural frequency, and then what? Or we define R. R is what? R is normalized. Basically, it's normalized this kind of frequency, right? For example, you define what omega equals 0 to 0.1, and then 0.01 to maybe 10. Right? And then we look at R equals what? R equals W divided by W and normalize here. So here, you see, we have generate that omega vectors, right? R is normalized frequency, right? And then our vibration amplitude, right, is what? X normalized, maybe X bar equals what? Look at our lecture note again. Sorry, I should show. Sorry, I got to share here. So I just show you basically we define our negative frequency equal to, right, and then define our omega vector from 0 to 10 seconds. The step delta omega 0.01, and then we get the R is the normalized frequency. Normal R is normal frequency, right? So that then we try to omega is vector divided by omega n. So this R is a vector with 1001 parameter, and then we look at the response, right? Response of this thing. Let me see about. Sorry, I need to check. How can I show? So basically, now we have this kind of basically we have some. I should close this window. Basically, you see, we have what? We generate this R is a vector, right? And then we need to calculate this one. How can we do? Basically, S bar equals 1 divided by 1 minus R squared. Oh, yeah, there's a 1. Then we basically look here. You see, now we generate this kind of another X bar, normalize the vibration response. Then we can plot this response. We can plot R and X bar. Okay, you see? And then we put 3. This is the vibration response. Why we can plot so that when then we can label this X label Y label is see. We demonstrate, show you about this kind of, sorry, okay. Now we just show you how to use MATLAB. So to generate this kind of, they call the frequency response function. Maybe put a title. Frequency response function response of one MK model without damping. Okay, you see, now I generate this kind of frequency response function for one big feeder MK model without damping. So that this is I don't do any question. It's not difficult, but it's worthwhile, of course, for all of you to learn about how we can use different methods to do this kind of analysis. Again, do you have any question? Any question? Huh? Of course, as I mentioned, sometimes you may want to do adjustment, huh? About things. Essentially, you know that sometimes this is too it's not very beautiful. Right? We need to do some additional tuning about that. Here, let me see. You can edit the plot. Let me share. Okay. See, I can edit the plot, and then we can try to adjust this kind of thickness and all things, so that this is something will be useful. Sometimes you want to generate this kind of thing, and then with marker, sometimes you want to say, okay, maybe marker here. Do that. Do some minor adjustment about the plot you do, and then the thickness. Sometimes you may want to make figures. You say, and different color, maybe red. Okay, so that I don't do any question about this thing, so that at least I think it's important for me to show you this kind of media tools. Okay, do you have any question for this example? All right, again, so that it's our lecture. No, looks like here, but still it's worthwhile for me to show you this thing. And of course, in reality, we can also try to plot what? Real time response. Time response vibration, a function of time. Right? Basically, you have these two components. One is the component related to force vibration. Another related to what? Initial condition. So that this is something you can easily. So basically, this is related to the force vibration. Right? And then this one with what? This one related to the free vibration from initial condition. Okay. And in reality, the total response will be combination of these two. Okay, so that something is here. And of course, we can also show you about this thing, so that you can easily again use MATLAB to do this analysis. Okay, and then of course in real things, so that you see, depends on the driving frequency of thing. Then if the driving frequency is larger than net frequency, you see this kind of response will be quite different. Okay. Okay, so here, this gives you some example how you can try to analyze this kind of time response. If you're given our mass is 100 kg, this 100 kg may be a car, a spring constant 1000 Newton per meter, and applied force is 100 Newton, and there's a driving force from the engine maybe is larger than net frequency by 5, and the initial condition is velocity 0.1 meter per second initial vibration here. So basically, we already give you the exact solution, so that if you try to use general solution, right, and then you can easily determine the time response and here, so that maybe it will be worthwhile for you to try to do how we use MATLAB to do this kind of calculation. And of course, there's another important thing. Why? One special thing is we care about if the driving frequency close to the natural frequency, what happens? In this case, sometimes they call the beating phenomena. Beating phenomena is if the driving frequency close, and then under some condition, we can find this kind of a solution. Vibration amplitude, a function of this sine omega t. That's the driving frequency from the engine or motor. This one, right? You see, epsilon is related to this delta omega. Natural frequency minus this driving frequency, right? So that you have this kind of thing, see? The kind of modulation. Yeah, so that is something will happen in real life. If omega epsilon is very close to zero, what happen? Huh? Is it close to zero? And you see, this will be somehow go to infinity, but it will not happen. Huh? So what happened? If our epsilon, the difference of the between this kind of driving frequency, omega, and then frequency close to zero, what happened? Huh? If this is zero, huh? What happened? Huh? What happened? So if this case, if you look at this MK model, so that eventually amplitude very big, right? But you will not go to infinity. Huh? What happened? What happened, huh? This is important for all of you to understand. Remember, this is we assume, right? This is what? We assume this is the model is the case without damping. If our driving frequency is curve here, right? Curve here, and then what happened? Huh? What happened? It's important for you to think about what happened, huh? In this case, actually, this model was not very precise. We assume no damping N and K, but in reality, in this real world, we always have some damping. So that in that particular moment, our model is not very accurate. We need to consider about the damping effect. Okay. So this is the important thing, right? So that you need to understand about the reality, right? So that this solution is for only valid for the case, right? Not exactly omega equals natural frequency. That's become resonance. Yeah. Okay, here I would say this solution is only valid for the case, right? Without damping, is that? So that if you're damping and then if you close to net frequency, for sure damping will dominate, so that your model is wrong. So that this is very important. Yeah. Okay, so this will lead to our another model. Another model, it means for the general solution is we have this kind of thing, right? Okay, so you see, it grow without the bound. This is doesn't help. You see, okay. Then you see, they go to infinity. In reality, it will not happen. There's no mechanical system in the world. If vibration amplitude go to infinity, because eventually you have some failure, right? Your airplane, your mechanical system will fail. So that something is important for all of you. Okay, I think we will run out of time. So that today we try to give you some brief introduction about this kind of frequency response, right? MCK model under harmonic vibration, and then how I can describe this kind of response, right? So this is one of the, I think, quite important things. Now you need to think about, right? Frequency response, a function of omega n, right? So that equals R. So that we try to give you this kind of concept, and this is one of important tool for practical vibration engineering. Okay. Okay, I think that's it for today's lecture. If you have some question, please I will encourage you to try to ask question on our Canvas website, so that this is an important thing when you do the homework, and then please try to add something on our Canvas website, so that that thing is important. Okay, I think that's it for again. If you, of course, for homework, it's something I believe is important for you to do some practice as well. So that's something is an important thing. Okay, I think that's it. Okay, bye bye. Bye bye.